Okay, very good. Thank you so much. And yeah, it's my pleasure to give this talk about twisted double bilayer graphene. And before I start, let me thank everyone who has participated in this work, especially Klaus Enslin, who was supposed to give this talk, but unfortunately couldn't make it. But also Thomasine, Julia, Elias, and Foko, with whom we worked together very well. And also great thanks to the theory support we had from Texas, from Jiangsu, and Al McDonald, and also from Aalto University, Jose Lado, who has been very supportive for parts of this work. So my first slide is about the zoo of moire materials. So you see this wonderful zoo that has been filled up since 2018, and probably the first correlated state that was put into the zoo was the Mott insulating state. And then the big breakthrough of the field essentially came with the discovery of superconductivity in these materials. Shortly after, ferromagnetism has been reported, and then there was quasi-crystalline structure that has been shown at 30 degrees twist. Topological channels have been discussed. There was some episode with superconductivity coexisting with ferromagnetism, but this left the picture quickly. Then there was a Chern insulator states that have been reported also in several materials. And today I'm going to talk about this one new member in the zoo, which is a density wave state. And there are, just to give you an overview, a few more predicted states like heavy fermions, valley helix states, frustrated magnets, and so on. So apparently, twisted bilayer graphene is a very interesting system to engineer some sort of correlated states. And the way this usually goes is one has band structure, and by twisting it, people manage to engineer very flat bands. And if the band is extremely flat, then the kinetic energy is no longer the dominant energy scale, and correlations can take over, and they will show up in very different manners. And today I'm going to show you a slightly different way of engineering a correlated state, and that is by bringing another band, say, into the vicinity in reciprocal space. And if the Fermi surfaces match in size and are displaced only by one Fermi wave vector q, then this is also sort of an ideal starting point to look for correlations. And this effect that correlations pop up in this sort of specific situation is called wave function nesting, and we will have a closer look at that later. But before, I would just give you a bit of an overview of the different materials that have been tried, and I will focus only on graphene. Of course, any other two-dimensional crystals can be twisted, and they also show correlated states. But everything with these in this field essentially began with graphene on boron nitride, which shows a supercrystal. Boron nitride is insulating, and the superstructure now affects the transport properties of the graphene. Then the twisted graphene, and now what I'm going to talk about today is twisted double bilayer graphene. That's essentially Bernal stacked or AB stacked graphene, ripped apart in the middle and twisted on top of each other. People also started to twist or to put a monolayer graphene onto a bilayer graphene with a twist. There are predictions that it could be interesting to twist the middle one, even though experimentally that's slightly more challenging. And then there are also structures where we have twisted bilayer graphene additionally aligned with the boron nitride, or ABC trilayer graphene on boron nitride. And all of these show this correlated states that I've discussed before. So the correlated insulator states popped up in most of these around angles of like roughly 1.1 degrees. Superconductivity has been discovered in a few. Ferromagnetism, usually in the other ones, and you see the ferromagnetism seems to pop up more likely if the structure is not completely symmetric, mirror symmetric around the middle plane, like this twisted bilayer aligned with boron nitride. Here, the double bilayer graphene, actually, when one applies an external field, it becomes also an asymmetric structure. Then the topological networks, which I'm not discussing today, but they pop up at tiny twist angles, essentially. And the Chern insulator states, and now the density wave states in this twisted double bilayer graphene, which appears in the intermediate angle regime. So it's not the small twist angle where the other correlated states have been reported on, but it's at slightly larger twists. And we'll see later why this is important. So here, just for completeness, there's been like where all these states have been reported on. You can have that slide later. Now, let's look at what this twisted double bilayer graphene actually is. So we start with Bernal stack bilayer graphene, and we put another Bernal stack bilayer on top. And now the twist angle can be changed towards a small angle, and then all of a sudden, magically, a Chern insulator state or a ferromagnetic state pop up, or even a superconductor, even though I think this is now out of the question. And what we're doing is to increase the twist a bit to the larger angles. And what we gain by this is that the wave function starts to be better layer polarized. What I mean by this is that you have a distinct wave function sitting in the top bilayer and another one sitting in the bottom bilayer. And you can control these now using top and bottom gate electrons. And with this, we can make this nested state out of an electron and a whole Fermi surface. So apparently it's crucial to have this layer polarized wave function, but how would one experimentally detect it? For this, it's probably good to understand how our devices are built. So usually we start with a bottom graphite backgate, which is insulated with a boron nitride layer from the active structure that we want to measure, which is the twisted double bilayer graphene in that case. Put another boron nitride contact layer, and we contact the entire structure, and then we can measure the current through this device. And now we add gates, so there's a gate electrode to the graphite, and we can have some local gates like this one, and by this we can tune the Fermi energy up and down in the system. And the structures are usually etched, and we add another layer of aluminum oxide, which is insulating, covers everything everywhere, plus a layer of gold, which is then a global top gate. Now, for the simplicity, you can just think of the structure as being like this. So there's a global top gate and the global back gate, which now can tune the electric field from the bottom to the top layer and the density in the system. So we can have now either sandwiched in here a small or a large twisted device. So I said for the large twist angle, the wave function is decoupled or layer polarized. So that's like having two bilayer graphenes. Whereas for the small one, the wave function is spread over all four layers, and we're in sort of a coupled regime. Now, if you look at the band structure, for the small twist, you can have the Brillouin zone of one bilayer graphene, which has this parabolic dispersion, right? And then you just twist it by the twist angle, which adds another cone from the other layer. And this, if the twist is large, and these cones are far apart from each other, they don't talk to each other so much. In the tiny case, it's essentially like having tetralayer graphene. Now, for the experts in the field, I know that the way I depict the tetralayer graphene is not entirely accurate. So, but for the sake of simplicity and for the sake of the argument, I think it's still helpful. Now what we will do is to apply, say, a voltage, a different voltage to the back gate, -5 volts, then to the top gate, +5 volts. And by this we have an external field, which I call D, pointing from top to bottom. And what this will do to the band structure, well, in this case here, you will see it shifts the cones up and down. So it just puts the top and the bottom layer on different energies. And additionally, it opens a band gap here. And this gap opening just comes from the fact that I have bilayer graphene, where a gap opens under the application of an external. And the tetralayer case, or if everything is coupled essentially, then I will just open a general gap. Now, let's look at what happens in back gate versus top gate. If I now take a map of these voltages, then you see if I sweep the two gates together, then I change the density of electrons that I induce in the system. And if I go in the other direction, so +5, -5, then I change the displacement field, the field from top to bottom. Now in the coupled case, I will see essentially a line where the density is 0 if my Fermi energy somewhere sits here in the middle, right? So this point would be a point of high resistance, density is 0, and the field is large. Now the situation, I can go down in density or up in density to reach the valence or the conduction band. Now the situation is of course different in the decoupled case. So if I now apply this voltage difference here to the top and the bottom, then you see that my Fermi energy now cuts the two bands. So actually I'm in some sort of conductive state, right? And I have lines where the density is 0 that have now a different slope in this gate-gate map. So, and the different slope comes from the fact that, say, the wave function at the top is tuned stronger by the top gate, and the wave function at the bottom is tuned stronger by the back gate. And again, I can reach the situation where I go everything in the valence band, sorry about that, or everything in the conduction band, and I can tune like this. So I will see two distinct lines as opposed to just one. But now let's go to the experiment. So here is the data conductance as a function of these two gate voltage, top gate voltage, bottom gate voltage at large twist, 10 degrees, and at small twist, 1.1 degrees, which is in the coupled regime. And you can see that you have pronounced features that follow these sort of opened triangles that I've shown before at the large twist, and everything is sort of parallel to this main lines here in the more coupled case. Now, there's one thing special that you might notice, and that is that the conductance is very low here in the center if both voltages are low. But this is something we don't expect, but which is interesting on its own, because apparently if you just put two bilayer graphenes on top of each other, and you don't apply any voltage, then the thing is gapped for some reason. And this gap can be explained by the sort of asymmetry of the bulk to the surface, whereas the bulk consists of the two inner layers and the surface are the two outer layers. And now the outer layers, they're attached to a boron nitride, right? Whereas the inner layers see two graphene layers in their close proximity. So their electrostatic environment is slightly different, and that leads to a charge transfer from the outer to the inner layers. And now you see you have, even without applying anything, you will open up a band gap by this small electric field that pops up. And this is what we see here. You can also see that if you follow this line, then it seems that some gap gets closed. And in fact, this is the gap in the bottom layer if we counteract this internal crystal field. The other thing I want to put my fingers on here is that in the middle, we're in a regime where we have electrons in the top layer, right? Oops, here, no, it's the other way around. Holes in the top layer and electrons in the bottom layer, right? So that's between these two zero density lines. But the conductance remains high in this case, as one would expect by just looking at this single particle band structure. We can confirm sort of that we have electrons and holes here at this large twist by looking at the Landau fan plots. So what we do is we take a cut here at constant fields, displacement field D, and we sweep the density versus the magnetic field. And then you see these lines emerging, and that's the Landau fans. And they have opposite slope and point to these two points here. So that means that the charge carriers turn in opposite direction. And it actually means that we have indeed a coexistence of electrons and holes here in this intermediate regime. What we'll now do is we go from this 10 degrees towards a smaller twist angle of 2.3 degrees. And the main thing that this will do is it will make the bands a bit heavier because the bandwidth gets smaller, and this will have a rather drastic impact on what pops up now. But let's first characterize the device at 2.3 degrees. Again, I show top gate versus bottom gate voltage. Now everything is recorded at a magnetic field of 1.5 Tesla, because then you see some sort of oscillations, Shubnikov-de Haas oscillations, which tell you how the Fermi surfaces look like. And I took the numerical derivative just to make these oscillations appear a bit clearer. Now, also in this case, we see two main features coming from the top layer and the bottom layer. And you see that also the Shubnikov-de Haas oscillations in this regime, they are parallel to this line or to the other line. So also here, you have two wave functions that you can tune in the top and the bottom layer, and which behave rather independently. But the question would now be, what is this additional thing here that pops up, say, at a finite density? So to get the band structure a bit better, we now look in more detail at the simple sketch that I have shown before. So I already said we have two bilayer bands from the top and the bottom layer, and these now form a new mini Brillouin zone. And of course, if you now would draw these parabolic bands a bit further, they would touch at some point. And this gives a different band structure than the one I've shown here. It will look more something like this. And now kappa prime and kappa are just the labels for essentially the top and the bottom mini Dirac points. So this band structure looks like the band structure of bilayer graphene. The main difference is that the energy scale here is much, much smaller. So we're on the order of 200 MeV. So that's also much larger actually than the bandwidth that you get at the magic twist angles where the bands are extremely flat. So this band is not very flat, but it's also, it's somewhere in between. So if you now draw the Fermi surfaces that you have here in this regime, the two parallel lines in the Shubnikov-de Haas oscillations correspond to the kappa and kappa prime points. If you look at the hole resistance, which is positive in this case, and this leads to slopes pointing upwards in B versus N. Now these lines here, which have the slope parallel to this main density line here, they have opposite slope and opposite hole resistance. So these are holes, and there's only one Fermi pocket, and that's the Fermi pocket that goes around the gamma point. So you have a transition here from kappa electrodes electrons to gamma electrons, and this transition is called the Lifshitz transition. It's a topological transition that is very typical for this Morris systems and has been reported on also in very different materials. What is now a bit different here is actually that we can open up band gaps with the external field. So we have discussed already this cut here at 0 displacement field, where the band structure has these two parabolic bands that touch at some point. So if we cross this point, then we cross the Lifshitz transition here. But now if you look at the band structure at finite external field, then you see, this is what I've sketched before, that you shift the energy in the top and the bottom layer, plus you open up band gaps. And you can now see that there are new regimes here and here, where there's only one band. And having only one band means that the other one is completely gapped. So, and this becomes more pronounced towards larger external fields. So this, in some sense, is a perfect mini-valley filter, because here in this regime, in the dark blue regime, you have both valleys present, the kappa and kappa prime valleys, and then by just putting in some electrons or removing electrons, you can enter a regime where only one of the mini-valleys is populated or only the other mini-valley is populated. So this is indeed sort of the ideal valley filter that one could wish to have. Now, for the rest of the talk, we'll focus on this inner regime here, where you see that the two bands, the electron and hole band, they coexist. So again, what we have here in this yellow regime is that we can put holes in the bottom and electrons in the top layer. And we can now look again at the Shubnikov-de Haas oscillations in this case. So here V versus N again, and look at the slopes. And also here you see that you have these two opposite slopes. So this just confirms that you also have electrons and holes in the system, just as you would have expected, and in a similar way as it was before at the 10 degrees. There's now one pronounced difference, and this is the large peak in resistance that appears exactly around zero density. So remember before, zero density in between here was always conductive at 10 degrees twist. But now here, there's a large peak in resistance appearing. And we can now check a bit what this resistance peak does with temperature, for example. So again, zero density here in the single particle band structure lies here. And if we now change the temperature from 1 Kelvin to 10 Kelvin, you see that the resistance becomes completely flat at 10 Kelvin. So this looks like a thermally activated gap. And indeed, it follows nicely the Arrhenius law. And this allows to extract the gap size of 0.4 MeV here from thermal experiments. So this single particle band structure is apparently not correct. But around zero density, there is now a new gap opened, and this gap must be opened by correlations. So indeed, if one looks at Hartree-Fock calculations, and these calculations have been done by Yang Su and Alan MacDonald, if one puts these bands into the Hartree-Fock machinery, then you see that there's a gap opening here. So these dashed bands here are exactly these bands that you see here. They're not just put on top of each other. And you see with the correlations, which are the solid bands, there's a gap open. This gap opens by electron-electron interaction. And this is because of this nesting. It's also expected that something like this happens at zero density. If we would look at the density of states here, it would look probably something like this. So particles get pushed out of this gapped region, and then you would have these peaks in the density of states and something gapped here at zero density. Why do I show this? Because we can now also apply a bias voltage to the system between the source and the drain electrode. And then you can sort of enter different states. For example, if the source and drain electrode are both still in the gap, so if I don't apply a very large bias, I'm still in a resistive case, but now I can sort of enter a situation where my conductance should shoot up. This is when I enter these coherence peaks here, or where I just enter into something conductive, and this is when my bias is actually larger than the gap. Now let's look at the measurement. So this captures rather well what we also see here. So the conductance has peaks at a certain voltage here, and then goes down to something resistance, and this rather symmetric bias here. And this really happens at zero density and at a very large displacement field. So this is also sort of consistent, at least, with the picture that a correlated state is formed, which pushes out electrons from this intermediate gapped region. What is now interesting, and what you can do with these systems, is to tune the parameters very, very well, because everything happens or occurs at low densities. So by just changing the density, I can now change these nesting conditions. So let's look again at the band structure here and the Fermi surfaces at zero density. So at zero density, I find two Fermi surfaces which are exactly the same. So you can connect them with one single nesting wave vector Q. So they really lie perfectly on top of each other. And this sort of favors this correlated state. But now if you go to large densities, then you move up in Fermi energy, and the Fermi surfaces don't match anymore in size, right? So one gets larger, the other gets smaller. And indeed, in the transport, you see nicely how this correlated state disappears. Now, what this peak here is that appears, we have absolutely no idea. So this would be the nested wave function, and this here at finite density, the not nested wave function. And we can play nicely, and I would just in the remaining minutes show you one example where one of these games one can play with these wave functions now. For example, applying in-plane magnetic field. So at zero in-plane magnetic field, these are the Fermi surfaces that we have discussed before. And now if you start to apply a magnetic field in the plane, then we will Zeeman split the bands, right? And now you have bands shifted up and down in energy by the Zeeman energy, which now gives two Fermi circles of equal size here at finite field. So the solid ones and the bit blurry ones, they have the same size. And you see that they have opposite magnetic moments. So this gives already influences sort of the spin pairing in the system. Now, interestingly, you now also find Fermi surfaces of equal size at finite density or at finite Fermi energy. So if you go to a certain density up here, then you see that same magnetic moments now have the same Fermi surface, and the same thing, but for the other magnetic moments at lower densities. So how does this show up in the transport? Now let's look again at the resistance peak as a function of density and finite in-plane magnetic field. So here, 0 Tesla in-plane field, this is just the resistance peak that we have discussed. And now if we start to apply a large in-plane field, then there is this shoulder of resistance emerging here on both sides of the main peak. And the emergence of this shoulder really follows the Zeeman splitting. And we interpret this now as here only part of the wave function being gapped, while the other remains conductive. So you see you have these 4 bands. 2 of them are gapped, but 2 are not. So that's why the resistance just reaches a certain value, and then, but not the same maximum value it has at 0 density. See also that the peak at 0 density stays in size. So we can now associate the spins to that. So we have same spin wave functions here and opposite wave functions in the middle. So we have now created correlated states with a certain spin texture. And this, we can now sort of play a bit with this by using this local top gate again. So I can now, for example, tune my system into a 1 spin configuration below the top gate and another one outside.
2 more minutes, Peter, thank you.
Yes. Sorry, 2 minutes?
Yes, around 2 minutes, please.
That's perfect, yes. So we can have now opposite alignment of these spins and look again at the resistance now as a voltage of this inner and outer gate. And just as a small reminder, if I tune only the inner gate, I would see an increase in resistance by going through this transition here, which is sort of this shoulder that you see. I call this increased delta R1. I get delta R2 for the outer one, which is here. And then I can see whether the total resistance here, if I tune one to spin up and the other to spin down, whether this total resistance exceeds the sum of the 2. And indeed it does by roughly 40%. So that's sort of at least in accordance with what we would expect from the picture that I've shown you before. It's also possible to apply parallel magnetic field and to do a similar thing with the actual valleys of the system. So to form valley pairing and make valley polarized states here. I'm not going into this detail, but I would rather finish my talk by showing you these last 2 slides. That is, in this intermediate angle twisted device, we apparently managed to form these density wave states, which are somehow, can also be called excitonic insulator because they're formed out of electrons and holes. Whereas in the middle here, we have this crystal field state, which is a single particle effect and has nothing to do with correlations. Now, the question that I haven't answered until now is why this intermediate twist angle is so important. And you can see it here. On the one hand, we want to have a good layer control. So this is the layer polarization, which gets better towards larger twists. And on the other hand, we want to have a large effective mass because that favors correlation. So the correlation strength increases towards smaller twists. So there's a range of intermediate twist angles between 2 and 3 degrees, which favor these correlations that I've shown. So as opposed to the flat bands, we can now control the nesting at small, sort of larger twists and form correlated states by this. And this leads me to my summary. So I've shown that in twisted double bilayer graphene at the intermediate angles, the wave functions are nicely layer polarized. This gives us very good gate control and allows to sort of match electron and hole Fermi surface. And it seems to be also very interesting for valleytronics because we have these valley polarized bands here. And finally, it has led to the, well, what we believe is a density wave state here in this intermediate twist angle formed out of electrons and holes. And with this, I would like to thank you for your attention. And now we certainly have a bit of time for questions.
Okay, Jorge, I don't know, you were in charge of questions. I don't know if you're there.
Yeah, hello. Well, there's only one question so far in the group chat, which is actually mine.
Yeah.
Yeah, well, first of all, thanks for the talk. It was really, they are really beautiful results, very clean.
Thank you.
Yeah, my question goes is about the device itself, the devices that you use. So if I understood well the figure where you were showing the device fabrication process, you are using top contacts. So the electrodes which you use to inject and detect current
Yes.
are fabricated on top of the boron nitride, right?
No.
Okay.
So, so the contacts are actually these guys here at this, and these are these one-dimensional side contacts.
Oh, okay, okay.
So the current passes from here to here, but then we just tune the Fermi energy by these global gates that we have.
Yeah, okay, then I misunderstood. So there is no need for you to use four-contact geometries or anything like that?
Well, there is, but there was no need for me in the talk to make.
I understand. Okay. All right. Thanks. And also, I guess these results are very strongly dependent on the quality of the device, right?
Yes. So it's not, well, yes, but I would say any group who knows how to make nice stacks can make these this sort of, or can engineer these states. So it's nothing which has extremely high demands on the quality. Especially what is different as opposed to this magic angle devices is that here you have really a range of twists where it works, right? So I've showed data of a 2.3 degree device. It also works at 2 degrees. The results look very comparable, and for the magic angle devices, you really need to be at exactly the right twist. And already 0.05 degrees off makes a large difference.
Okay. Thank you. We have also now another question by Enrique Diaz. So he asks, have you studied the band structure in the exciton insulator regime?
Well, so the only thing, maybe this plot here summarizes a bit, what we can study by Shubnikov, de Haas oscillations and so on, is actually the single particle band structure. So we can essentially confirm that we have electrons and holes. And you see the same happens here at this larger twists where we also have electrons and holes. That's the same plot. So you look just at the slopes of these Landau levels that emerge, right? But what we see now is that if we have these electrons and holes, there's a large resistance peak at zero density, just in this regime where you have the coexistence and where the single particle band structure is not gapped. And this peak is thermally activated, so it's a band gap. So by this, we just know that we can sort of confirm this single particle band structure. And then from this sort of infer that if at zero density there is a resistance peak thermally activated corresponding to a gap, if this happens, then the system sort of forms a correlated state. So that was our reason. I hope it's clear.
Okay, so as far as I can see, there are no more questions.
Well, yeah, thank you so much, Peter. Then I think it's time to move on to the next speaker. So the next speaker is José Luis Hernando for Complutense University of Madrid. So José Luis, could you please start sharing your screen?
Yeah, can you hear me?
Yeah, and you if you might also turn on the video, would be much appreciated. Thank you.
Okay. I would like to make a quick comment. So in case anyone prefers to ask questions by themselves, I think there's we also have the possibility to open the microphone for somebody in the audience. So just please request it in the chat, and we can also do that. Yeah, sorry for the interruption.
Well, so thank you for the presentation. And also, I would like to thank the organization to give me the opportunity to make this speech. I'm going to talk about the spectral properties of a disordered surface of a topological insulator. But first, I would like to thank also my partners, Yuriko, Elena, and Francisco, for all the help and for teaching me about during all this process. So let's start with the talk. Those are the principal points I'm going to talk about. Let's start with a brief introduction. It's well known that between it is well known that in the interface between a topological insulator and a trivial insulator, which could be maybe the vacuum, appear some surfaces states which have a Dirac ultrarelativistic band dispersion. Well, so what happened to those states if our topological insulator has impurities randomly distributed? Well, so what happened? Exists a lot of approximation to treat this case, but we are going to focus on two of them. The self-consistent Born approximation, which is the most common used, and the CPA. Both of them are self-consistent approximations, so that's why we focus only of those. Well, so let's review first some of the principal properties of those surfaces states. Those states are described by a 2D effective Hamiltonian, which accept a continued description. So as I said before, they have ultrarelativistic band dispersion. Its self-state has a momentum spin connection, so which is also a typical property of the topological insulators. And also I would like to remark that the local density of states depends on the energy by an absolute value. Well, so now let's make a diagrammatic description of our problem. We are going to introduce the impurities by a disordered potential. Since we use a 2D continuum model for the surfaces states, we need to manually introduce a 2D lattice where we are going to situate our impurities. So, so we are going to ask our potential to have the periodicity of this lattice that we introduce, and also this potential will depend on some random variables which are going to talk about the different configurations that we could have. Well, so since we are interested on the spectral properties, we are interested in the Green function. The Dyson equation for this system is written like that, but also it can be written in a serious form when the Earth terms looks like that. And in fact, it's a disordered system, so we are interested not just in the Green function, so in the average of this Green function. As we saw, the dependence on the average value is on some product of this structural factor, which contains information about the different configuration. And we can calculate for the first terms and take some conclusions. In first place, we can appreciate the dependence with the concentration of the impurities. As we saw, the principal contribution, since the value of the concentration is less than 1, are for those processes where only one impurity appears. No? Also from those calculations, we can extrapolate some Feynman rules, as we saw here, which let us calculate the higher orders of this average gain function in a more comfortable way. So, for example, here we have the zero order, the first, the second order, and also the new one, which is the third order, calculated by a diagrammatic description. Well, also this admits a self-energy description where the self-energy contains all the information about the scattering process. So diagrammatically, it will correspond to take in account all the fundamental interaction with the impurities. Diagrammatically, it will correspond to those diagrams. And we are interested in calculate this self-energy. So how we introduce the impurities in our topological insulator. We introduce them by non-local separable potentials, where for the safe function, we choose a step function in the momentum space. And why is that? We introduce in this way because we are assuming a one-band model to our calculations, and this also reminds us that the electron moves originally in a lattice, so it has a finite wide band. So also in the real space, it will correspond to the Dirac deltas, so it's a realistic description of the problem. Well, also for the coupling constant of the potentials is the random variable which we are going to treat. And for this random variable, we are going to suppose a surface disorder because it's easily to treat with it and has probably all the information that we could obtain. Well, so for the self-energy description, we replace this Hamiltonian through an effective Hamiltonian where the potential is replaced by a self-energy term, which also consists in no local separable potential, but now all of them has the same coupling constant, which is the self-energy and is which we want to calculate. So first, before calculate this self-energy, we can get some properties of this effective Hamiltonian, but it's useful first define some new variables because in this way all of them have the same units. Well, now our self-energy consists in sigma, and diagrammatically this corresponds to absorb the first term, which is the self-energy which the virtual crystal approximation gives, which is another approximation to calculate in disorder systems. Well, so once those new variables are defined, we can get those properties of this effective Hamiltonian, which in this way doesn't say too much because we do not still calculate the self-energy. So now is where approximations came out. Let's start with the coherent potential approximation, the CPA, which consists to ask to the green function associated to the effective Hamiltonian to be equal to the average green function. Well, through an auxiliary potential, this transform into the condition for the transfer matrix. Its average value must be 0, and this also leads to a self-consistent equation. In this consistent equation, I would like to remark that asymmetry appears, which consists by changing delta by minus delta, and also the concentration by complementary. This is one less the concentration. Well, this has some consequences in the solutions and also in the local density of states. Well, diagrammatically, this self-energy will correspond to taking account all the Wiegand diagram, where the propagator between the scattering points consists in the average propagator. So now we can see in which consists the self-consistent Born approximation, the SCBA, that, as I say, is one of the most common used. This approximation consists in to solve this equation, which aims to make a cutoff in the series expansion on the delta series, and this equation replacing the potential and doing some calculation transforms into this self-consistent equation, which also can be obtained as a second order expansion in delta to the CPI equation. Well, in this case, there is also a symmetry, but in this case, it's like an artificial symmetry because, well, it consists by changing delta by minus delta, but in this case, without change the concentration. I say it's artificial because Keynes, as I say, assume a few concentrations, so the concentration and one less the concentration is quite the same, and also, which is more important, because we stop into second order in delta. Well, now let's see this diagrammatic description, which consists for those approximations taking account only the first weak diagram, again with the average propagator between the scattering points. So due to that, we expect that both approximations predict the same results for a few value of the disorder parameter, and it's what we obtain when we plot the solutions. And also, due to that, the local density of the states has the same behavior and the same values. Also, as the case without impurities. But what happens if we take higher orders of the disorder parameter? Well, in this case, we saw a significant difference between both approximations for the self-energy solutions. We saw that the SCBA predicts higher values for those solutions, which also it can be seen in the local density of states. Well, again, the SCBA predicts much higher value than the CPA, and both of them predict zero energy states. Well, before studying those zero energy states, I would like to remark that
2 minutes left, José Luis.
Okay, I would like to remark that by plotting the local density of states, a new symmetry appears, which consists for the SCBA by changing the energy by minus the energy without changing the concentration, and for the CPA by changing the energy by minus the energy and the concentration by its complementary. Well, this has consequences on those zero energy states. As we will see, we can plot those states as a function of the disorder parameter, and we saw a same behavior, but the SCBA again predicts higher values. Well, we can also plot as a function of the concentration, and again, higher values for the SCBA, and it seems to have the same behavior. But what happens if we let the concentration go over 0.5? We saw in this case that both approximations predict a different behavior for those zero energy states. While the SCBA predicts a continued growing, the CPAs, due to this symmetry by changing the energy by minus the energy and the concentration by its complementary, it's obliged to decrease on those zero energy states. So, in conclusion, what are the differences between the CPA and the SCBA? The CPA taking account all the weekend diagrams, where the SCBA taking account only the first one. Both of them do not predict an energy gap in the local density of states, and that's because the way that we introduce the potential without breaking the time reversal symmetry which protect those states, and neither predicts located states. Well, both of them predict some symmetries, but are different type of symmetries. The ones for the SCBA are more artificial, where the ones for the CPA is the one that we expect for the self-energy. Also, the one of the local density of states, which, as we saw, has some consequences at those zero energy states, which both of them predict. But both of them predict a smooth behavior with the parameters, but predicts also a different parameter where the behavior became significant, where those states became significant. But definitely, and the principal reason why the CPA is a better approximation is because the SCBA overestimates the self-energy and also the local density of states, and also the states at zero energy. So thank you so much for your attention. Is there any questions?
Hi, Jorge. Is there any question there?
Yes, so we have a question by Alberto Cortijo. Alberto, I don't know if you prefer to ask the question yourself.
Okay, yes, thanks, because it's a little bit long. So thank you for your talk, José Luis. So I have a couple of small questions. So the first one is that, as we know from graphene, interactions also lead renormalization of the Fermi velocity, which is the same as you find using the soda. So do you expect any other effect when you consider both cases? I know that this calculation turned out to be quite difficult, but do you expect some kind of feedback between the two when you consider both types of effects?
Do you mean the effect of the impurities and the other one, which will consist
and interactions?
So interactions. Well, actually, I don't know, but I expect that there is no a quite significant new behavior, just because if you depend on how you introduce the electron interactions, but if you don't break some important symmetry, I don't expect that appear some new thing. Only maybe change the shape or something, but I don't know.
Okay, just maybe if there is time for just another question is in the case of real topological insulators, quite often the Fermi level reaches the bulk bands. Okay, so how difficult would be to include also bulk bands in the calculation? So because this all can induce matrix elements between bulk and surface state, right?
I do not even consider to include the bulk on the calculation, because since we use a 2D effective model to describe those surface states, like this H0 Hamiltonian, we are completely not taking account the bulk. We only are focused on the surface states without taking account the bulk.
Yeah, so, it is more than enough. I do understand that. I just a question if you thought on this possibility.
No. Sorry.
Okay, thank you. No, that's fine.
Yeah.
So thank you so much. I think it's time to move to the next speaker. So
okay.
José Luis, thank you so much for your presentation. So the next one will be Yuriko Baba from the Spanish Research National Council, also on the Complutense University of Madrid. So Yuriko, so the audience is yours.
Yeah.
Thank you.
Hi, do you hear me? I think so.
Yes.
Okay.
Really nice and low.
So, hello everyone, my name is Yuriko Baba, and my presentation is going to be about some recent theoretical efforts on violent Dirac semimetals. More precisely, we study topological semimetals under external perturbations that break important symmetries of the system while preserving the surface states. In this way, we obtain a tool for tuning important properties of the states, such as the Fermi velocity or the spin charge of the current, connected with the chirality of the states. The main references are given here at the bottom, a PRB volume 100 and another paper in preparation. So before starting, I want to thank the organizers, and especially Mario and Jorge, for giving me the opportunity to share with you our work. And I would also like to acknowledge my collaborators. The results have been obtained together with my supervisors, Francisco Dominguez Alamacosta and Rafael Molina. And a special thanks must be extended also to my groups, CONG in the Complutense University of Madrid, and especially to Elena and Alvaro, here in the photo, and to the Condensed Matter Theory group at CSIC. I'm going to organize the talk in 3 main parts. I will start by introducing the materials and models. Then I will discuss the two perturbations considered, the effect of an electric field perpendicular to the surface, and the Rashba spin-orbit coupling generated by broken inversion symmetry. Then let's start by introducing with more detail the 3D topological semimetals we are interested in and their phenomenology, namely Dirac and Weil semimetals. In these materials, the conduction and valence bands touch at isolated points, leading to a gapless dispersion alongside an absence of Fermi surface. The touching points are called Weil and Dirac points, and between these points, arced surface states appear protected by topology and symmetry. In these surface states and their properties resides a great part of the interest in these materials. Here you can see a schematic representation of the bands of our Weil semimetals. Near the Weyl node, the dispersion relation is linear and appears as three-dimensional analog to graphene, and it can be described by a Weyl equation. The Weyl nodes are monopoles of Berry curvature, and the charge associated with them is called chirality. In this presentation, it is denoted by the Greek letter zeta. The robustness of Weyl nodes resides in the separation in the reciprocal space. In fact, Weyl nodes come in pairs and can only annihilate in pairs. Here you can see some experimental results alongside the theoretically obtained projection of the Weyl points for the tantalum arsenide family. If we focus on an effective low energy description near the gamma point, we can describe the Weyl semi-metal by a minimum model with two Weyl nodes. The minimal Hamiltonian is written down here, and its dispersion is plotted in this figure. The Weyl nodes are these ones, while the surface states are linearly dispersive, have a linear dispersion relation in X, and they are represented in red and blue. At a given Fermi energy, the surface states lie in open contours that form the previously shown Fermi arcs. Simple Hamiltonian like the former one can be used to build topological Dirac semi-metals. In fact, each Dirac point can be constructed by imposing two Weyl nodes with opposite chirality, leading to a net chirality equal to 0. In this scenario, the Fermi arcs come in pairs and connect the direct points, precisely as two copies of Weyl semi-metals. Compounds such as sodium bismuthide and cadmium arsenide shows this space of Fermi arcs, and the manufacturing of high-quality thin films and ultra-thin films of sodium bismuthide had made the material one of the most promising candidates for technological applications. Here you have some plots, experimental and theoretical plots for sodium bismuthide. So, here you have the Hamiltonian for the sodium-3 bismuthide obtained from DFT interpolations. The surface states are linearly dispersive only in X, while they are quadratic in Z. This is due to the inclusion of quadratic terms that break the particle symmetry, these C terms, and the important effect arises from the rupture of this symmetry, as we will see later. Finally, in this figure, we show the surface state obtained by diagonalizing the former models. They show the probability density in logarithm scale versus the spatial direction of decay of the states. The left side represents the minimal model. Notice that, depending on the model parameters, two kinds of surface states are obtained. We have states with pure exponential form and states with an oscillatory decay added. We refer to these two categories as tape A in orange with oscillations and tape B in blue with pure exponential form. Notice that in a finite slab, tape A states in opposite surfaces are more decoupled due to the oscillations, while tape B states are typically more hybridized. The transition between these two kinds of states is defined by the transition radius, which is a function of the Fermi velocity, and it is defined here. And moreover, the surface states exist only inside the gap, defining another radius of existence in the reciprocal space. So in this instance, we show both radii in the momentum space. In the right side of the slide, we show the sodium bismuthide states that are only tape B. Notice that the quadratic terms lead to a chiral-dependent radius of existence, as you can see here, and the decay lengths at fixed momentum are their chiral-dependent, and very different decay lengths are obtained for state with non-zero chi-x, as you can see in this figure here at the bottom. Now that other models have been introduced, we can go over to the perturbation. So, what happened to the Fermi arcs if you apply an electric field perpendicular to the surface? The idea was to start analyzing the minimal model, and the electric field in this model can be simply described by adding to the former Hamiltonian this linear term in 1. The F indicates the strength of the magnetic field, of the electric field, sorry. The system is finite in the direction of decay, and periodic boundary conditions are implemented in the other two special directions. Here you have a schematic plot of the setup. And in this side of the slide, you have the dispersion relation without electric field in the left and with electric field in the right panels. The Fermi arcs are these flat states and linearly dispersive states, and the electric field, notice that it does not mix the chiralities, but it breaks the spatial inverse of symmetry, so it leads to a splitting of the two cones of the opposite surfaces, as you can see in this plot here at the bottom. Studying with more detail the bands, we identify three main effects of the electric field. First of all, a shifting of the cones is induced, and as already mentioned, and this is simply related to the change of the potential of the surface. This first figure shows the shifting of the cones in the momenta versus the electric field. The second and more interesting result is the renormalization of the velocity due to the momentum-dependent terms that modify the slopes of the cones. The second plot shows the velocity renormalization versus the electric field, and in these both plots, both quantities are reported for a range of velocity corresponding to tape A in dotted line and tape B states in straight lines. The third point, very interesting also, is the surface state type transition that is a consequence of the two previous ones. Since the type of surface state depends on the momentum velocity, we expect that the electric field may induce a transition between different types of states. The red plot shows the transition from A to B and the conversion from an oscillatory decay, the blue curve, into a purely exponential form, the orange one. The transition from A to B is expected. In fact, the shifting in the momentum is the most appreciable effect of the electric field, more noticeable than the velocity renormalization. We checked also that the transition in the opposite direction from B to A do not take place because the momentum shift does not increase beyond the modified transition radius, and hence the conditions for type A are not fulfilled. The type transition may lead to a very large increase in the hybridization of the two surfaces in a thin film, and the coupling of these opposite surfaces is a necessary ingredient of the recently discovered 3D quantum Hall effect rising Weyl orbits. So we foresee important observable consequences of this transition in quantum Hall experiments. Now, if we move to sodium bismuthide, we found that the former results are reproduced along with new features due to the particle Hall asymmetry and the chiral dependent decay of the states. The particle Hall asymmetry leads to a displacement of the cones, not only momentum but also in energy, as you can see here in these bands. And most importantly, the dependence of the chirality of the states lead to a chiral dependent renormalization of the velocity, as you can see here. The two branches have very different slopes. Recent experiments in ultra-thin films performed by Collins et al. And cited here at the bottom have achieved electric fields of the order of few volts per nanometers in sample of atomic width. In order to implement our proposal, we need slabs of hundreds of angstroms, and due to this estimated thickness, we expect that lower fields can be achieved. Even for electric fields 1 order of magnitude lower than the ones obtained by Collins et al., we found that the velocity renormalization is a non-negligible effect. As you can see in the C and D panels, the renormalized velocity is more than 10 times the initial value for the positive chirality, while for the negative one, it only doubles. The renormalization of the velocity will have a direct impact on the electronic transport properties through the surface states of the thin films. In the case of sodium bismuthide, due to the chiral dependence, we envision the possibility for application to chiral electronic devices. And now, what happens if the electric field considered break an important symmetry of the system, as the up-down parity symmetry with a chiral coupling term? This is the second thing we ask ourselves. And the second perturbation we considered is within this scenario, and it is a Rashba spin-orbit coupling. The Rashba coupling is generated by the breaking of inversion symmetry in the surface, and it could be enhanced by the coupling with the substrate and controlled by an external electric field. The strength of the Rashba parameter is then directly related to the potential drop at the surface, and this possibility for control had been experimentally demonstrated in indium gallium arsenide, indium aluminum arsenide heterostructure, and mercury telluride quantum wells. In semimetals, the Rashba spin-orbit coupling have been explored in two-dimensional ultra-thin films of sodium bismuthide by Costa et al. At in bigger samples, the intrinsic effect due to the broken inversion symmetry in the surface is probably small and has not been observed yet in experiments. However, a carefully designed sample with a slab of topological semimetal on top of a substrate with heavy atoms should induce a strong and controllable Rashba spin-orbit coupling in the surface that will impact the Fermi axis. The possibility for spin-dependent transport of this scenario is the subject of this part of our work. In order to model the coupling, we add this HR to the Hamiltonians. Notice that HR couples both the electron bands, leading to a coupling between chiralities. And due to the symmetry breaking, the surface state turned into state with a more generic and complex spin structure. In fact, time reversal symmetry still dictates that two counterpropagating partners have orthogonal spinors, but it does not require equal spinors at different energy. We call these states general surface states, and here you have a simplified representation of the chiral surface states and general surface states and its energy-dependent spin orientations. We address the problem from a dual perspective. We obtain analytically the general surface state in an effective two-band model, and we study the transport properties within the Landau-Büttiker formalism implemented in Quant, a free open-source Python package for numerical calculations. Let's start with the analytic results. The effective Hamiltonian is obtained here for the surface state in the basis of the chiral state. The diagonal terms are the energy of the chiral states, while the anti-diagonal terms are the coupling between them generated by Rashba. The coupling is proportional to an overlap integral that we call G of k, and this G of k factor is very important. In fact, we obtain very different results depending on its dependencies. In the minimal model, G of k is actually a constant, and therefore the Rashba coupling generates a rotation of the chiral spin basis, but it does not have any crucial implication. The energy of the states resemble a 2D direct dispersion where the Rashba term generates an anisotropic velocity. On the other side, the sodium bismuthide has a GK that depends on the momenta due to the onset quadratic terms in the Hamiltonian. This dependence leads to a real chiral coupling that will have an important impact on the transport properties of the states. Here you have a plot of the two components of the general surface state in the chiral basis. As you can see, for increasing R0 and increasing momenta, the states are more mixed. In order to study effect on the transport, we obtain the conductance in a two-lead device. The transport setup is shown in this figure. The choice is justified by the intention of measuring the transport of the surface states only, as well as to match an experimental realization. The leads are bidimensional and metallics, and they are plotted in orange. In red, we mark the part near the coupled surface where the Rashba spinor coupling is considered, and in blue, we indicate the pure direct semi-metal without coupling. The device is designed to carry only the surface state current. In fact, as you can see on the picture on the left, the system reaches the expected quantized conductance in weighted peaks only for the surface states. Here you have three plots of the conductance for three different systems as a function of R0, or equivalently as a function of an electric field in the substrate. The total unpolarized conductance is plotted in red, the direct polarized conductance in yellow, and in green the spin flip conductance. The results for the minimal model
2 more minutes,
are here on the left. Okay, thank you. As I was saying, the results for the minimal model are here. As already predicted by the analytic calculation, the effect in the minimal model is trivial, and the conductance decreases, but no spin flip arises. By the other hand, in sodium bismuthide, the spin flip is allowed by momentum-dependent rotation. Therefore, for high field, the spin flip conductance becomes dominant with respect to the direct polarized one, as you can see here for this range of fields. Moreover, the accurate choice of the system size of the slab can increase the effect due to the contribution of multiple surface states modes that arise from the finite size effect. In this way, we can design a proper chiral spin-rich device based on surface state without an appreciable loss of the conductance amplitude, as the example here at the bottom. In conclusion, we have proposed two main different ways of tuning the chiral surface states of a topological semi-metal, both based on external fields and with direct impact on the transport properties of the states. In the first part of the talk, we discussed the effect of an electric field perpendicular to the surface. We found that it modifies the bands, displacing them and reshaping the cones. Moreover, the Fermi velocity is changed in a chiral-dependent way, and this may have important effects on the transport of the states. Furthermore, a type transition can be induced, increasing the hybridization of the opposite surfaces in a slab and improving the connection between them. In the second part, we discussed the Rashba spin-orbit coupling, an interaction connecting once more with an electric field, but now local on the surface. This coupling generates a mixing of chiralities and the possibility of a chirality flip. Most importantly, we have shown that the accurate choice of the system can exploit this coupling to design a chiral switcher. A special effort has been made in order to propose experimentally feasible scenarios and devices, and this way we hope to draw the attention of theorists and experimentalists in order to make this proposal a measurable reality. Thank you very much for your attention. And I don't know if there's any question.
Thank you, Yuriko, for your nice presentation. Is it time for questions now?
Yeah, so far we don't have any questions in the chat.
So I have a question myself, Yuriko. Is it possible that you use this, your...
Sorry, there's...
Yeah, go for it, go.
Alberto, do you want to ask it yourself?
Sorry, yes, thanks. Thank you, Yuriko, for your talk. I found very interesting the result you found. So I have a question concerning, perhaps it's related more to what we are going to listen in the following talks. So what you found is that depending on the chirality, you find a relation between chirality and a spin renormalization of the Fermi velocity, right?
Yeah.
So for instance, what happens if you take one piece of bind semi-metals and consider the surface states and you illuminate with circular light? Do you spin?
Yeah. Actually, it's a very good question, and I think that there is going to be a contribution by Rafael Molina in Novel Quantum Materials, I think.
Okay.
Colloquia about this idea of illuminating with polarized light
because then you expect some kind of chiral selective spin propagation, right? Because the Fermi velocities are different, so
yeah, surely, but
okay.
I will have to think a little more about it.
Okay, yeah,
just
that's because yeah, it's just a kind of follow-up question, I guess.
Yeah.
Oh, thank you.
Sorry, Yuriko. Yeah, I had a question myself as well. Is it possible that you use your system or your packages you're using with just to compute different spin orbit, like instead of RASPA, like Edelstein, any other kind of spin orbit interaction?
Sorry, I didn't get the question completely. You mean if we can use, for example, this to compute spin orbit coupling? No.
Yes, materials with not only RASPA spin orbit interaction, but any kind of spin orbit interaction. So can you just try to use them? Is it easy to implement them?
Yeah, theoretically, surely it's very easy. And I think the device is quite general and just a 3D device in a three-dimensional system. So I think that the answer is yes, surely.
Okay, thank you. Thank you so much. I don't know if there are more questions. If not, then we are perfectly on time to continue with our show. So no more questions. So thank you, Yuriko, once more. Yes? Is there any question?
No, there's no questions.
Okay. So thank you, Yuriko. Now the next speaker this morning is Andreas Augustolius. But now, hopefully you are ready. Hi,
hello.
Andreas. Good morning.
Can you hear me?
We can hear you. We can see you. So could you please start sharing your screen, and then the audience is completely yours.
Okay. Can you see the slides?
We can, yeah. Thank you.
Okay.
Beautiful. Thank you so much.
So, hello, everybody. My name is Andres. I'm a PhD student in Vilnius University in Lithuania. And first of all, I would like to thank you, all my colleagues who also worked with me on this research. So today here I will present charge carrier transport properties and thin film hybrid field effect transistor structures. And most of the data today I will present is from our recent published article in Synthetic Metals. Okay, so in this work we worked with PCP-DTBT material. The whole name you can see in the here. I won't read it. So basically, it's a material, a whole transporting material, were synthesized for solar cells to transport the holes, and usually is there's the formula, and usually is mixed with PCBM to form a heterojunction for solar cells. But we took another approach. We only worked with a single layer. So what we did, we used a simple spin coating procedure to form even thickness layer on the substrate. And we ended up with this kind of structure. I call it hybrid field effect transistor structure because we have organic layer as an active layer, and we have silicon dioxide, which works as a dielectric layer. Because usually there could be field effect transistors for with the organic dielectric layer as well. So yes, and we chose a top electrode structure because in this way we can measure charge carriers in both directions, Y and X, which I will call perpendicular to the substrate, which is Y, and parallel to the substrate, which is X. And in our case, gate electrode was used silicon, highly doped silicon layer as a gate electrode. So in this work, we basically used two main techniques. for investigating charge carrier mobility. So first is called ISOLIV, or injected charge carrier extraction by linearly increasing voltage, which was developed by a professor from my university, Gytis Juška. So in this case, charges are moving from the electric layer to the source contact, so it's y direction or perpendicular to the substrate. In this case, the setup is quite simple. We have generator and oscilloscope, which are connected to the active layer. So with the ramp voltage, we inject charge carriers, and then we extract them with this linearly increasing voltage. And two main things I should say. These are the transients from our work, from the sample, for different temperatures. So injecting voltage and extracting voltage should be enough for the transients to reach the 1.5 initial step, or 2 times initial step, which is here, which is initial capacitance step from the ramp signal. So with these values, then we can have the thickness of the layer. So with this method, we not only can find the mobility of charge carriers, but also the thickness without any other methods like spectro, like AFM or similar. So, and having this E value, we can find the transit time of the holes, and then eventually to find the mobility, which is perpendicular to the substrate direction. The other method we used was current transients. In that case, holes are moving near the electric layer in the X direction or parallel to the substrate direction before they are extracted via drain contact. So in this case, we have this setup, which gate is grounded and drain is grounded via resistance, which and then the signal, the square signal, is put on the between to the source contact. So and these are the transients also from our sample at different temperatures. So the two main things also from this transient. So it's TD, which is time when first holes are moving through the channel of the field effect transistor and reach the drain contact and are extracted through the drain. So here we see no current, and then it starts increasing. So it means that this time, when the first holes have traveled through all the thickness, and then we can find the mobility of them in the parallel direction. And also we have the maximum current at we can have the saturation current, which is maximum current in the field in the channel with the applied voltage. And so using those two methods, now we can talk about the direction, different directions, different movement directions of charge carriers. In our case, in all cases, it was the holes. So the polarity of the voltage was such that holes would move and would be extracted from the sample. So using those two techniques at room temperature, we measured 3.5 times 10 in the power of -3 in the parallel, mobility in the parallel to the substrate direction, and the perpendicular we've got 4.2 times 10 in the -6. So we see around 800 times higher mobility near the dielectric layer than in the perpendicular to the substrate direction. So this kind of non-linear behavior was not a surprise, but an interesting result. So we dig further and we did the temperature measurements. And the temperature measurements, what we did, we measured through the whole heating session. So we started at room temperature and we heated, and at each point we measured the mobility in both cases, because we can easily switch between the method because the setup is quite similar. So we could do this live, as to say, in the heating session, all the measurements. So two things here, that the mobility itself is higher at the parallel direction, but around 72 degrees Celsius, it starts to decreasing really fast. So this was another interesting point of this material. And this red line shows the energetic disorder parameter, sigma, which comes from Basler's Gaussian disorder, Gaussian distribution of density of states, and in which he showed in his Monte Carlo simulation that is how the charge carriers are moving through the organic layers in general. So when you have the Arrhenius plot, which is a log-log scale for mobility and temperature, you can have this parameter calculated, which is real tied with the mobility. This picture I borrowed from Baranovsky article. He did a good review about all the mechanisms of the of the transport of the charge carriers. So it was interesting for us because usually we knew, we saw other works with this material, that this material can be highly crystalline under some circumstances. For example, for manufacture, there were works where researchers made highly crystalline layers by using some kind of solvent, a vapor, during the manufacturing process. So, and they got like really high crystal structures. Our approach was different. We wanted to use a simple method to inspect the material itself. So then we continued with morphology measurements, because it's quite interesting, and we wanted to see whether it shows any crystallinity. So on top, A and B pictures are from unheated sample of AFM, and on the bottom there are two pictures of heated sample after the heating. So what we see here is we don't see any distinct crystallinity of the layer. What we can see, which is expected, of course, that the heated sample was smoother, because delta Z is just 1.3 nanometers, before it was around 5 nanometers. So we see that it's smoother, which is expected after heating, but we didn't see any thickness changes. So, because as you saw from the formula, we can, lively inspect the mobility and every time to check the thickness of the layer, so we can have the results if the heating, sometimes it affects the layer and it gets, thinner. So we didn't notice any of that. So what we did next, we did XRD measurements, and as well, we didn't see any points where it would show highly crystalline structure in a direction. So this was interesting, and we then thought that since we did measurements in higher temperatures, we should see how the digital scanning calorimetry and to do of the material, and it showed that around 112 degrees Celsius there is glass transition temperature of this material. So these lines show this corresponds to these lines. So around this, it starts to change in the morphology. So from this parallel, we can see that the heating affected the morphology, and that's why it started to decrease, because they move in a thin area near the dielectric layer, and every small change in the morphology is crucial for those holes to transport. And in this case, where they move perpendicular to the substrate direction, they move in the bulk material, and it's already, the disorder is different and the morphology is different in this direction. So the thermal activation is bigger. So we see like the increase in the mobility in all the heating area, all the heating in all the temperature, where we see no decrease. So it's, yeah. So just to sum up, what we got is that the whole mobility are 800 times higher than in parallel, than in direction, than in perpendicular direction, and that similar energetic distort parameter in both directions indicate that in parallel to the substrate direction, lower average coordinate intersite distance, or in other
Well, I think it's breaking the line, Andrews. Or is it just me? The one is not able to hear it?
I think we have lost him. Yeah.
Yeah, well. Hi, Andrews. I think we lost you for a bit, and now you are muted. Yeah, the line was breaking.
Okay, is it okay now?
Yeah, no,
could you please start again with the summary? Well, no, not from the very beginning, of course, but summary.
Okay.
Yeah.
Okay, so yeah, so the second point is that we basically showed that we have a better molecular orientation, or for better conditions for the whole transport in parallel to the substrate direction. And we basically believe, more like it's based on the study in general of these kind of polymers, that when you spin coat them, they tend to lie on the surface, and they form like an edge-on or very similar orientation, which basically means that more path is traveled through the backbone of the polymer, while in perpendicular to the substrate direction, it has to do more jumps between other molecules, and it's the conditions of the transport is not as good as in that direction. And that due to morphological changes in higher temperature, mobility of holes moving near the electric surface is decreased. And this is an interesting point for the people who are manufacturing these kind of solar cells or field effect transistors, because usually ambient temperature is it's quite low, 72 degrees. So in the sun, you will definitely reach it. And it's really, you have to, address this issue if you are making, the samples. So I would like to thank you for your attention. Thanks to this conference organizing committee for letting me, present my data in these unusual times. And this is our home. This is the center where I work, Center for Physical Sciences and Technology in Vilnius. So thank you.
Thank you, Andrews. Thank you so much. Now it's time for questions, please.
Yeah, so far we don't have any questions in the chat.
I would have one, well, actually two. So one is the mobility versus temperature. You see there's this kink in the mobility at 72 Kelvin. Now, yeah, if you repeat the measurement, how does it look like? Like, is it reversible? Or?
Yeah, so we did also like the repeated where should I did put, yeah. So as you can see, we did the second heating, then cooling, then third heating. So after every heating, we see like this kink, and then the morphology changes, and then when you are cooling, it goes like smaller mobility with the same temperatures to go out smaller mobility. So at certain point when you don't heat enough, it's reversible. But when you heat too much, the morphology changes again. For example, third heating, it repeats this curve, the second, the cooling curve, and then when you reach more temperature, it's already starts, to change the mobility as well and morphology.
Thank you. And my second question would be, how do you put the gold contacts? like without destroying the material or so? Is it easy?
This Arquine standard procedure. It's evaporated via vacuum through the mask. So it's done in vacuum and
any adhesion layer or something?
Sorry?
Any adhesion layer, or is it just pure gold?
It's pure gold.
Okay.
Usually the gold is very good for injecting with these HOMO and LUMO levels with the material. With most of the polymers, gold is good for the whole transport investigation.
Thanks.
Well, I don't know if there are more questions. Well, if there are no more questions, we would like to thank Andres again once more. And now it's time to move to the last part of this session, which is more related to SIS. It's going to be introduced by Ron, who has an invited presentation, Ron Amount from the Weizmann Institute. So, yeah, thank you. The audience is all yours, and I know that we are going to enjoy your talk. Thank you so much.
So, you see my screen?
Yeah, we can see it and we can hear you nice and clear.
Okay, very nice. So, thank you. And I'm going to tell you today how chiral molecules can be non-linear spin devices. And it's really interesting to consider such a small system, like few nanometer maximum, to be a non-linear devices, but I hope to demonstrate it to you. So if you consider electron transmission through chiral molecules, the simplest way to think about it is to think about helical potential, an electron going down this helical potential. This is one electron picture. And you realize that because of the curvature, there is a force acting perpendicular to the velocity of the electron. In the rest frame of the electron, this force is exactly like a magnetic field, like a Lorentz force. And therefore, one can consider in the rest frame of the electron as if the electron feels a magnetic field, effective magnetic field. And this effective magnetic field can act now on the magnetic moment of the electron, on the spin. And basically, we get this effective magnetic field is related to the velocity of the electron and the field, the electric field acting on the electron. The electric field changes signs for the two enantiomer, namely if it's right-handed or left-handed helix. And the velocity, of course, changes sign when you go one direction or opposite direction. So what we realize that the effective magnetic field flip signs upon changes the enantiomer, the handedness of the molecule, and the direction of motion. And now this magnetic moment acts on a spin of the electron, stabilizes one spin, and destabilizes the other spin, and therefore we get spin selectivity. This is basically the picture that appears in many, many theoretical works. And of course, it's a single electron picture. It's a nice picture. It has some truth in it, but it doesn't provide the extent of spin polarization that we observe. And I will show that we need to add to this picture something that has to do with the non-linear behavior of the molecule. So this effect of spin selectivity, we call it the chiral-induced spin selectivity, and it is, or cis effect, and it has many manifestations. And let's see an example. We can put a molecule or molecules on the surface. The surface can be magnetized, either with the magnet pointing up or down. Then we come with a tip of conducting AFM, and we can measure the current flowing this through this molecule as a function of the voltage applied and as a function of the magnetization of the substrate. And here you see results obtained for either a DNA, in this case it's DNA of different length, and you see a 20 base pair, namely a short DNA, 30 base pair, 40 base pair, and what you realize, of course, that there are two curves here, one for when we measure when the magnet is up, the other when the magnet is down, and we get spin polarization on the order of 50%, and here you see the same results on a semi-log scale, and then you realize that the two spins have different threshold for conduction, and of course that the conduction is not linear. We can get these results also for oligopeptides. That's for people that are not familiar with these terms. Basically, this is a helix, like small protein. And again, in the oligopeptides, we see length dependence, almost linear, length dependence of the spin polarization, and we get spin polarization of the same order of magnitude as we observed with the double-strand DNA. Now, interestingly, this spin polarization that we obtain, remember, the molecules are really short, as you see, maximum 3 nanometer, but still we get very high spin polarization at room temperature. Another interesting finding is that if the same experiment were performed with photoelectrons, namely not conduction, but photoelectrons, namely unbound electrons that are leaving the surface, going through a monolayer made from these molecules, and the spin polarization was measured. This work was done in Münster by the group of Zacharias, and they find the same order of magnitude of spin polarization. So it's quite amazing that independent if the electron is bound to the molecules or not, we get about the same magnitude of spin polarization. And what we can monitor also is the spin-dependent, length-dependent transmission. And what we observe here, that while for one spin, the transmission decays very fast, for the other one, it decays much slower. It's again long scale. And this means that one spin is transferred more ballistically than the other. And the question is, how come? So we have to remember that in this model, the spin is coupled to the linear momentum. Therefore, backscattering means that the electron has to switch spin in order to be scattered back. So if the electron has the preferred spin, it will go with very little backscattering. However, if the spin is not preferred, the backscattering will be very efficient. That's a really very similar to the effect observed in topological insulator. So if I summarize our results so far, we see IV curves that are not linear. There's different threshold for each spin conduction, indication for no spin flipping, namely during the conduction, spin doesn't flip. That was observed also in the photoelectron experiment. The polarization is similar to that obtained with photoelectrons. So let's see on what properties of the molecule the spin polarization depends. So here we join forces with the group of Bert Meyer in Eindhoven. And the group in Eindhoven synthesized these molecules. They are large molecules that have side groups. And these large molecules tend to make supramolecular structure, wire-like structure, as you see here. Now, here, what is called R here means these groups, these molecules, if you wish, and these groups can be chiral. And what Myers group find that when the chirality of these side groups define the handedness of the supramolecular structure. So if these side groups have one chirality, one handedness, the wires will look like right-handed helix. For the opposite handedness, the wire will have opposite handedness. So that's nice. So you can make these wires with chiral molecules and get chiral wires. You can also use achiral molecules, then you don't have specific chirality. Okay, so what we observe, we make these wires, we put them on the surface of the same type of AFM I mentioned before. So we have this wire lying on the surface here. And now we come with the tip of the AFM and we measure, first of all, the thickness of the wire. And please realize we are speaking about wires that are lying on the surface. So we measure the thickness perpendicular to the length of the wires, namely along the diameter of the wire. And you realize that the diameter here is on the order of 15 to 20 nanometer. And now we can measure the spin polarization. And here are the results. You see that the spin polarization, it's very significant. And what is clearly, the polarization is huge. And here you see the spin polarization calculated. The spin polarization means here the current for one spin minus the current, the opposite spin over the sum. And you realize that for a specific molecule, we can get up to 90% spin polarization. So remember, 20 nanometer, room temperature, 90% spin polarization. It's a huge number. And so the results are very impressive, but we can do something in addition. What we can do is to make these chiral molecules and mix them with achiral molecules, namely molecules that are not chiral. And then they form, again, these helices. But what you realize that when you measure the optical activity of the helices, that's the optical activity, which is proportional, if you like, to the amount of chirality. You see in the beginning, if you mix very few chiral molecules into the achiral molecules and you form wires, the optical activity increases linearly with the number of chiral molecules, as expected. However, when we increase a little bit more the number of chiral molecules, we get what the group in Eindhoven likes to call surgeon and soldier effect, namely that the chiral molecules, that surgeon, they force the soldiers to form chiral structure. So we get amplification of the chirality, and the optical activity depends non-linearly on the amount of chiral molecules. So this effect is known for many, many years, and it was shown here too. But now we can measure the spin polarization for this type of wires. And here is the spin polarization measured for the same type of wires. And you realize, and that's a big surprise, that the spin polarization actually follows the optical activity. So you please appreciate the fact that optical activity, it's a non-local property. It doesn't depend on a single molecule, it depends on the supramolecular structure. And here we see that the spin polarization depends also on some property that it's not a single molecule property. And these results are consistent with other studies that we and others performed and found that there is correlation between the optical activity of the molecule and the spin polarization. So what we know so far? We know that spin selectivity due to this effect can be very high. By the way, the effect was observed also in 2D perovskite films about 80 nanometer thick. The effect is proportional to the optical activity of the material. Backscattering suppressed for the favored spin. So immediately when you see spin and chirality, you think, what about magnetism? And the idea is to see if we can affect by the cis effect, magnetized surface. So what is the concept? When molecule is approaching a surface, due to the difference in the electrochemical potential between the molecule and the surface, the molecule gets charge polarized. This, you may remember, it's the induced dipole effect, right? The surface induces dipole in the approaching molecule. Now, because the molecule is chiral, the induced dipole means charge is redistributed in the molecule. The charge is redistributed on the helical potential, and therefore there is a spin polarization. So actually, each electric pole now is associated with a spin polarization. Interestingly, if you have one enantiomer, in this case you have left-handed helix, you realize that the spins in the negative pole is pointing down. However, for the right-handed helix is pointing up. So there is enantioselectivity, Henden's dependence of the spin polarization on the electric pole. Now, if this molecule is approaching a surface, and the surface is ferromagnetic, let's say, you realize that we expect different interaction for a surface that the spin pointing up, because now the interaction will be a low spin interaction, or what we call singlet type surface, while if they are pointing the same direction, it will be a triplet-like energy potential surface. And that means that there is different energy. In order to bind it to the surface likes to be in this configuration. In this configuration, binding is forbidden because of the Pauli principle. So let's see what happens. We take chiral molecules and we pattern the surface and we absorb chiral molecules on the surface. And here you see an AFM image of the adsorbed molecules. You see we have these squares. You see the L means left-handed, optically left-handed molecule, and that's right-handed molecule. Please, I call your attention that here the squares are not as nice as here. And the reason is that here we use natural molecules from nature. Nature is very pure L-type. In this case, it's amino acids, L-type, while the D amino acids were made in a synthetic way, and it's very difficult to make them as pure, therefore they don't form such a nice squares. Okay, so we have two structures, and we see the topography of the structure. Now we can come with a magnetic tip of an AFM and measure the force. And what we find that for one handedness, we get the magnetic moment of the molecule pointing up. For the other handedness of molecule, the magnetic moment is pointing down. So why is this? Please look here again. In order to form a monolayer, namely forming of monolayer reduces the free energy of the system, it's worth for the ferromagnetic layer to flip spin and align so that it will be anti-parallel to the spins on the molecules. So for one handedness, the spin is pointing this direction. In order to bind the other molecule, it has to point to the opposite direction. Now we can see the effect in another interesting way. We take ferromagnetic substrate, we put on the ferromagnetic substrate very thin gold film. On top of the gold film, we absorb current molecules. Now we come with what it's called Kelvin probe. Basically, the Kelvin probe is a very simple concept. There is a surface. We vibrate the surface relative to the substrate. And because the potential, the electrochemical potential on the surface is different than the electrochemical potential on the substrate, we get current flowing when we vibrate. We can, of course, then zero the current by applying voltage. This way, we learn about the different voltage or the different work function, if you wish, of the substrate and the reference in the Kelvin probe. We use two types of Kelvin probes, either macroscopic one or one that is based on atomic force microscopy. And here are the results. What you realize here, that if we take molecules that are right-handed, like here, you see that for the right-handed molecules, we get for the North Pole, we get higher work function than for the South Pole. For the left-handed, we get the opposite. And if there is no chirality, it's of course the same. So what it means that the efficiency of charge flowing into the molecules upon applying the electric field due to this surface that vibrate, upon applying this electric field, the efficiency of charge flowing into the molecules depends on the handiness of the molecules and the spin in the ferromagnet. So it confirms what we observed before, but in a dynamic way. And here you see how it depends on the length. So you realize that for DNA, the dependence on the length is not linear. For the oligopeptide, it's linear. And the reason is that in DNA, it's not only the polarizability depends on the length, while for oligopeptide, it depends on the length square, sorry, while in the oligopeptide, the polarizability depends only on the length as is. And this is beyond the scope of my talk here. So the question is, what is missing in the model that I presented before on the Cis effect? The model does not explain the very high large spin polarization. And many people thought that the reason is that somehow there's a problem with the spin-orbit coupling, that the actual spin-orbit coupling is larger than the one we calculate. The typical number used in the calculation is around 5 milli-electron volt. 5 milli-electron volt gives typically spin polarization of few percent, 6-7% maximum, while if we take very high spin orbit coupling, then we face another problem that the spin is not a good quantum number anymore, and actually we lose spin polarization altogether. So spin orbit coupling by itself is not the solution to the problem. The model that I presented before cannot explain the relation to the optical activity. Now, very interesting indication for the right model was given by work of Jonas Fransson, and basically he realized that if you put electron correlation into the model, the results start to look more like the experiment. The theoretical results look more like the experiment. So I will try to give you a simple, without equation, simple picture of how the Cis effect works. And before doing it, I want to put your attention on several problems that exist in general when people calculate conduction through molecules. Typically, when conduction through molecules is calculated, one solves the electronic state of the molecules, very much like in mesoscopic physics, and then apply the voltage. However, in molecules, actually, when you apply field on the molecule, you change the molecule. The field itself changes the overlap between the atomic orbitals in the molecule and changes the energy level of the molecule. So this approximation is not a good approximation when we try to calculate conduction through molecule. So the difference between mesoscopic solid and molecules is severalfold. One is the size. Because of the small size of the molecules, typically the charge or the potential applied on the molecule is not screened completely. So all the molecules feels the field. Now, when molecules in contact with the surface of other molecules, its electronic state are attenuated in order to equalize the electrochemical potential. And this is a result of the fact that typically the density of electronic state in the molecule is lower, much lower than in the electrodes. Now, when we apply electric field on the molecule, we see there is a Stark shift, and when the electrons or hole are passing through the molecule, they themselves affect the electronic structure of the molecule. So it's clear here that a simple linear model that assumes that we have electronic state, and let's calculate now transmission through this electronic state, this picture is not correct. And we have to take something which is different, something that includes the fact that we apply electric field, and this electric field affects the molecule. Okay, so here is the model, and I will try to explain it briefly. Let's assume that we have chiral molecule here, and it's between two electrodes. Actually, it doesn't have to be electrodes. If on the two sides of the molecule there is some species with different electrochemical potential, it behaves like electrode. Now, only because of this, there is a field applied on the molecule. This field charge polarizes the molecule. Of course, when we apply external electric field, this can be even higher, so we get a field applied on the molecule. The first thing that happens when field is applied on the molecule is charge polarized due to its polarizability. Now, because chiral molecules has an anisotropic polarizability, it means that the polarizability is spin dependent. I don't want to go into it in details, but the polarizability is spin dependent. As a result, we get, if you wish, momentarily, a two type of charge distribution for one spin and for the opposite spin. So now you realize, even if the difference here is few percent, let's say 3, 4, 5%, now electron has to move into the system. The electron that has to move in, if it has the same spin as the electron that was left behind here, the energy is basically the exchange energy between the two electrons. In molecules, it's an order of 1 electron volt. So even if you have, let's say, 4% spin polarization here, time 1 electron volt, it means 40 milli electron volt energy barrier for injecting the wrong spin in. The right spin will go in with no problem. So we realize here that due to the polarization of the molecule, we get, if you can like to call it, spin blockade that hindered the injection of the wrong spin into the system. And this type of spin blockade enhances the polarization as I described in the beginning, which is basically a linear effect. So we have here a non-linear effect due to the polarization and then for the spin injection. So the difference between molecules and macroscopic solids is the size. As I said, it has to do with the density of state. Varying the electric field shifts the level, and the electrons or hole themselves affect the structure. Hence, the simple model that I discussed before is simple wrong, and the conduction is definitely never linear, never depends linearly on the voltage applied. Now, what is important here is to appreciate that the polarization that I don't know what happened here. Okay. The model that I just described provides two things. First of all, it gives us the large spin polarization we wanted because it gives us different barrier. Secondly, the spin polarization depends on the anisotropic polarizability of the molecule. And the anisotropic polarizability of the molecule is exactly the same term that's going into the optical activity. Hence, we can understand now the relation between the cis effect and the optical activity. Important observation, we don't need coherency in order to see this cis effect. And indeed, cis effect was observed by now in a very thick samples of up to 300 nanometer and thicker. In summary, chiral molecules, because of their topological properties, are very efficient spin filters. The effect results from many electron interaction. Spin exchange plays an important role both in the effect itself and the interaction of the chiral molecule with other molecules or with surfaces. Here are the people that really did the work, and their dedication made everything possible. Here are the many collaborators we have all over the world that are both great scientists and great friends, and thank you.
Thank you so much. Thank you, Ron, for your really nice presentation. I think there's time for plenty of questions, and I can see there are some of them already popping in. So please, Jorge.
Yes, so yeah, so there's a question by Carmen Maya Giraldoni. So she asks, how come in the self-assembly spin polarization results, the spin polarization is not zero at zero bias?
It's not what?
Zero at zero bias.
The spin polarization, it is typically zero. Of course, okay. It's typically zero bias. In the curves I showed, the curves don't go to bias to zero because we have no information about the zero. Now the zero is not really zero because there is some shift due to the induced the dipole moment between the self-assembled monolayer and the surface, but basically in the effective zero potential, the spin polarization is zero.
Okay, thank you. I have another question myself, which is, so when you were showing the results for this Sargent-Soldier effect, in both in the spin polarization and in the optical activity, the plots showed a drop when you had 100% Sargent molecules. The values were lower than, for example, for 80%. Can you?
Yeah, it's interesting. The truth is we don't understand it. You know, I want to show you it's very close to the noise level, but in principle you're right. We noticed it. It's within the signal to noise, but I think it's real, and we don't completely understand it. It has to do something. Apparently, it has to do with how the polarizability change. You can imagine, for example, that if the polarizability, the simple polarizability of the achiral molecule is larger than that of the chiral molecules, then the optimum for anisotropic polarizability is not necessarily 100% chiral molecule. So you can imagine how it comes. We never checked it, but can be a reason.
Okay. Yeah, I see your point. Thank you. So as far as I can see, there are no more questions in the chat.
No, I think there are no more questions. So we can just then thank Ron again for his beautiful talk, and probably move to Shu Yang, who's like penultimate talk of this session this morning. Hi, Shu, could you please, yeah.
Yes, can you see me and can you hear me?
We can't hear you, we can't see you. Now we can.
Okay, great.
Sure.
Okay.
Morning, thank you so much.
Thank you. Let me share my screen.
So Shu Yang from the University of Groningen, if I'm right, is going to present some results also on CIS.
Yes. Okay. Can I start?
Yes.
Yeah. Okay. Thank you very much for the introduction, and thank you, Professor Naaman, for a very detailed overview of the CIS effect. I will now continue with this topic, and I will talk about how we can detect this very exciting effect in two-terminal spintronic devices. And in particular, I will emphasize the fundamental symmetry requirements on the type of signals that can possibly arise in these type of device-based experiments. Let me see, how do I go to the next? Okay. So yeah, I guess I don't have to introduce the CIS effect again. I show here only a very phenomenological description of this effect. Essentially, it describes that when we send a bunch of spin unpolarized electrons through a chiral molecule, and what we get out of it is a net spin polarized flow of electrons. And to put this in spintronics terms, what we have here is a charge current being converted by a chiral molecule into spin currents. So essentially, this is a type of spin charge conversion mechanism. And these spin charge conversion mechanisms are what the spintronics field is very interested in, because it directly relates to spintronic applications. But there are some questions about the CIS effect, two questions in particular here I want to talk about. The first one is, how is this CIS effect generated within a chiral molecular structure? So what is the microscopic mechanism of CIS? And Professor Naaman already talked about a few theoretical proposals, and there are a lot of theoretical discussions going on, and I believe the next talk will be also talking about just this. So I will skip this question, and instead I will focus on the second question. How can CIS be detected in experiments, and in particular, two-terminal electron transport experiments? So in these experiments, typically we obtain IV curves like that. And as Professor Naaman pointed out, these IV curves are never linear. They're highly non-linear IV curves. But the beauty of these type of experiment is that even within this non-linear curve, we can identify a linear response regime that is close to zero bias. And there we have a lot of implications from fundamental symmetries. And we can talk about what these implications are and what these signals must behave within these different linear and nonlinear regimes. So this will be the focus of my talk today. And since I mentioned the chiral molecule is essentially now, we describe it as a spin charge conversion mechanism. And it is natural to think about using another spin charge conversion mechanism to detect it, and that is ferromagnetism. So this is indeed how most of the electron transport experiments are done. We have two electrodes, here right and left electrodes, and in between them we have a chiral molecule that provides spin charge conversion, and a ferromagnet also provides spin charge conversion. And the common interpretation of these experiments is that when we drive a current through this circuit, the chiral molecule will generate a spin accumulation here due to the charge current. And then this spin accumulation can be detected by the ferromagnet as a charge voltage signal. And of course, here, if you reverse the magnetization direction, you would expect different charge voltage signal, and hence you get a magnetoresistance signal over here. However, there is a fundamental problem with this interpretation. It's that according to the Onsager reciprocity, this type of MR, particularly in this type of device, so two contacts, one ferromagnet, this type of MR cannot arise in the linear response regime. And this is because there's always a reciprocal process going on where it is the ferromagnet injects a spin accumulation over here, and it is the chiral molecule that detects this spin accumulation as a charge voltage. And in the linear response regime, so close to zero bias, these two processes, they compensate each other exactly. So the net result is a zero MR signal. So what is this Onsager reciprocity? It is a set of fundamental symmetry relations for coupled thermodynamic processes, and it is derived from the microscopic reversibility. And since we're talking about electron charge and spin transport, and these processes are thermodynamic processes, and thereby they are governed by Onsager reciprocity. And to understand the implication of Onsager reciprocity for two-terminal electron transport, we can envision this simple picture over here. So we have, let's say we have one electron and we want to bring it from position 1 to position 2 via a certain pathway. And we have a magnetic field B in presence. And then if we consider the time-reversed situation of this entire process, we're now bringing one electron from position 2 to position 1. So we reverse the motion, and then at the same time, we reverse the magnetic field. So now it's minus B. And these two the time-reversed processes, for the electron, they experience the exact same pathway. So they experience exactly the same resistance. And this is indeed one of the most fundamental requirements of Onsager reciprocity on two-terminal electron transport experiments, and that is the two-terminal resistance that you measure, it cannot change when you reverse the total magnetic field. This is a very fundamental requirement from Onsager reciprocity, and it is very strict in the linear response regime. And to understand this, we have to understand the fundamental difference between a magnet and a chiral molecule. And that is, a magnet breaks time reversal symmetry, while a chiral molecule does not. And since we've been already talking about both the magnet and the chiral molecule as spin charge conversion mechanisms, so we are interested in how this difference translates in terms of spin charge conversion. And to describe that, we introduce transport matrix formalism. So basically, we want to describe the transport of charge and spin, and they're also coupled, so we use a matrix to couple them together. And the driving forces of this transport for charge, it is a charge bias, a voltage bias, sorry. It is an electrochemical potential difference between the electrodes. And for spin, the driving force is a spin accumulation. It is an electrochemical potential difference between the opposite spin species. And what these driving forces generate is a net charge current as well as a spin current. And then we have this matrix here to couple them together. So all these four terms, they're coupled together by this matrix. So this matrix over here, it captures the spin charge conversion properties of either magnet or a chiral molecule. And we're interested in how they're different for these two guys. So if you run through the mathematics, which you can find in our paper here, I will not go into details. And the result is, for magnet, you always have a matrix that is antisymmetric. So the off-diagonal terms, these two terms, they have the same value but opposite signs. And for a chiral molecule, you have these off-diagonal terms that always have exactly the same value. So this fundamental difference in terms of time symmetry is now translated into the symmetry of the matrix. It is antisymmetric for a magnet and symmetric for a chiral molecule. And then with this, we can actually calculate the two terminal conductance in these type of experiments. Again, we have two terminals, a magnet, a chiral molecule, and here we introduce a node where we can measure the electrochemical potential as well as the spin accumulation. And again, we can run through the mathematics, which I will skip over here. And then what we get is the two terminal conductance that is indeed dependent on these off-diagonal terms of this matrix. Yeah, both this and this guy, and also these off-diagonal terms over here. However, it depends on these terms only to their square. So this is this term squared. So it doesn't depend on the sign of these off-diagonal terms. And what the sign tells us, the sign of this off-diagonal term here tells us about the magnetization direction of the ferromagnet. And the sign of this guy here tells us about the chirality of the molecule. So this equation over here essentially tells us that the two terminal conductance does not depend on the magnetization direction or the chirality in the linear response regime. And as a result, there cannot be MR or magnetic resistance in the linear response regime. So can we now still detect this effect or chirality using this type of experiment? And the answer is yes, but then we have to look beyond linear response regime. And one of the most commonly encountered nonlinear transport mechanism is, of course, tunneling. And here we have a ferromagnet interface, a tunnel interface that provides this tunneling mechanism. What I show here is the energy diagram of this tunneling process. We have a ferromagnet on one side, biased as a chemical potential μL, and then on the other side is the node where we introduced before. To the node, the chiral molecule is connected. And for now, we'll be only looking at this part. And this node provides an energy relaxation process so that we can define a spin accumulation in the node, μs. And I will show you now that this energy relaxation is actually the secret that we can generate an MR signal in a nonlinear regime. So for that, we have to be looking at the reciprocal processes of spin injection and spin detection by the ferromagnet. For spin injection, we're talking about all the electrons that are flowing through the ferromagnet. And that corresponds, this is the tunnel transmission probability as a function of energy. So what we're talking about spin injection, it's relevant to all the electrons underneath this blue curve over here, within this entire biased opened window, delta mu. So we're talking about this entire region over here. However, the reciprocal process of spin detection, it is only sensitive to the spin accumulation, which is now over here. And we see now for the two reciprocal processes, we're actually talking about electrons at different energies. And that's why we're able to break Onsager reciprocity in the nonlinear response regime. And with this, we can actually calculate the IV curves obtained through such a system. And this is what I show you here. We have two IV curves corresponding to opposite magnetization directions. What we see is two IV curves are different at high bias, nonlinear regime. And as a result, there's an MR signal. Note that I call it, this MR signal is the difference of the two curves divided by the sum. I call it MR because it does not necessarily corresponding to the spin polarization. So we have the MR signal that is finite at high bias. However, as we go to linear response regime, so as we go to low bias, go close to zero bias, these two curves have to exactly overlap each other. And as a result, the MR signal has to vanish at zero bias. So what I tell you here is that the key to generate this MR at nonlinear regime is energy-dependent transport, tunneling, and then energy relaxation in the node. And what we're talking about here is only the nonlinear mechanism at the ferromagnetic tunnel interface. We haven't talked about the nonlinear mechanism in the molecule yet, and we're already able to get this MR signal. And then the next, we also have, of course, nonlinear mechanisms inside the chiral molecule. And here, for example, the transmission through molecular levels, either the HOMO level or the LUMO level. I will skip the details here, but the result is very similar. So due to energy relaxation, we have now two IV curves corresponding to opposite magnetizations that are different at high bias. However, the two curves will exactly overlap each other as we go down to low bias regime, close to zero bias, and the MR signal, it can be finite at high bias, and it must vanish. It must be zero as we go close to zero bias. And our conclusion here is that the MR can indeed arise in the nonlinear regime, but it must vanish in the linear response regime. And the sign of the MR depends on chirality, the charge carrier type, so whether you go through LUMO or HOMO, and then the bias direction. So how does our conclusion compare to other chirality-related effects? And there's one known effect that is that can detect chirality using electron transport experiment, and that is called electrical magneto-chiral effect. It is discovered by Riken in 2001, and it essentially describes that the resistance of a chiral conductor, it depends on chirality. So when you put it in the magnetic field B, it depends on chirality, whether it's D or L chiral, and then the charge current flowing through it, and then the magnetic field B. So it tells that we can detect chirality using magnetic field. And if you look at the IV curves that I showed you before, we have now two IV curves that merge into each other at low bias regime, and they do not cross each other. So the blue one is always on top. So if you write down the resistance of these IV curves, there is a term that looks exactly like that. But instead of magnetic field, we now have magnetization N. So what we have to notice here is that this chirality dependent term here, it is a first order correction to the linear resistance, which is this guy over here. So that this chirality dependent part is only observable in the nonlinear regime. And then what we show here, the role of magnetization suggests there's actually a role of spin transport in this phenomenon. And another property, another phenomenon is called absolute asymmetric chemical synthesis. So it is a chemical reaction where we start from a non-chiral reactant or a racemic mixture of equal amount of opposite chiralities. And in the product, we have more of one chirality than the other. And it was also known that this type of imbalance of chiralities cannot be induced by a magnetic field. However, it was pointed out by Baron a very long time ago that in fact, that requirement was only concerning the linear response regime. And if you go away from equilibrium, if you go to the nonlinear regime, this absolute asymmetric synthesis can be induced by a magnetic field. So what these two processes tell us is that they agree with our conclusion that a magnetic field or magnetization can indeed detect or even separate chiralities, but it can only do so in the nonlinear regime. So can we now still detect this in the linear regime? And the answer is yes, but we cannot rely on magnetization reversal anymore. And here I introduce one geometry that is a chiral spin valve. So we have now, instead of a magnet, we have both components that are chiral molecules, and one of them can switch chirality from D chiral to L chiral. And what we see here is the two-terminal resistance changes as we flip the chirality. And it can even happen in the linear response regime. And that's because now we have two elements that have the same, that are described by the matrix with the same symmetry. And I show now two IV curves corresponding to the two configurations. And indeed, even at a low bias, close to zero bias, we have a finite signal. And then it can be further enhanced as we go to nonlinear regime, go to higher bias. So a chiral spin valve without magnet can detect cis in the linear response regime. And alternatively, we can use a multi-terminal geometry. And here we show a device, 4-terminal device. It has a channel, conduction channel that has spin charge conversion. Here it's generic. It doesn't have to be cis, but it can be cis. And then you put a magnet, 2 magnets on top. And then you can see a distinctive 3-state spin valve signal. It's different from the traditional spin valve where you have 2 states. And we also introduced multi-terminal geometries before. And here I show chiral molecules as the spin charge conversion channel. And we can use either 1 magnet or even without using any magnetic contacts. And we are still able to detect cis in the linear response regime. So multi-terminal geometries can also work in the linear response regime. Now this brings me to the conclusions. I showed you that the 2-terminal detection of cis as magnetoresistance signal is indeed possible, but it's only possible in the nonlinear regime, in the high bias regime. And that 2-terminal MR signal must vanish as we go back into the linear regime, close to 0 bias. And then this nonlinear MR signal can arise from energy-dependent transport and energy relaxation, and the sign of this MR depends on chirality, charge carrier type, bias direction. And finally, if we want to detect this in the linear response regime, then we need to forget about the MR signal. Instead, we can look at a chiral spin valve geometry or multi-terminal geometries. And with this, I will leave the conclusions over here, and I would like to thank you for your attention.
Thank you, Hugh. Thank you so much for this really nice talk. Now is it time for questions?
Yeah, so there is a question in the chat by Giuseppe Ingla. He says, thank you for a nice talk. I am curious about how is the linear response defined for a chemical reaction?
Okay, this is a good question. So basically, it's linear response in this case is talking about how far away we are at the equilibrium state. So we start from equilibrium before the reaction, and it has to go over a barrier, and then go back to equilibrium. And what it says is that only when the system is away from equilibrium, there can be a different reaction rate towards different chiral enantiomers. And if we have an amplification process in this equilibrium, for example, crystallization, and then we can, because of this amplification, we can attain this non-equilibrium feature back into a final product.
Okay, thank you. So far there are no more questions in the chat.
Yeah, I think we can then. Thanks, Hugh. Oh, yes, sorry.
Wait.
You said that still.
Yeah, you said, do you prefer if I just turn on your microphone and you ask yourself?
Sorry, what?
No, yeah, I was asking Giuseppe if he wants to ask the question himself, because he's having follow-up questions. So. Well, anyway, I will read it myself. So he's asking, okay.
So yeah, I just found the microphone thingy. So I was wondering if this is only related with the shape of the minimum at R. So basically this sort of parabola like here. So the linear response here is only some small region here where you have your laser pointer, and that's it.
Yes, linear regime. So the range of linear regime can differ, depends on the system, but it has to always be there because that's close to the equilibrium. How close, it depends on the system.
Okay, thank you. Yeah, that's clear.
Okay, then if there are no more questions, we can then thank you again for this really nice talk. And we go to the very last talk of this mini-colloquia, which is going to be given by Elena Diaz from the Complutense University of Madrid, also related to cis. So Elena, floor is yours.
Good afternoon. Let me share the screen properly. Yeah, is it okay now?
It is indeed, yes, thank you.
Okay, thank you very much. So good afternoon. Thank you for the introduction and thank you for organizing this nice online meeting that is working so well so far. So here my talk will be devoted to this topic, thermal and disorder effects in chiral-induced spin selectivity. And this work has been performed mainly at the Universidad Complutense de Madrid by me and Francisco Domínguez Adame, and also in collaboration with Rafael Gutiérrez from the Technische Universität in Dresden and Vladimiro Mujica from the Arizona State University. So this is the outline of my talk. I will start with a brief introduction to the phenomenon we've been talking the last talks, SES. And later I will present the main theoretical tools I've used to model some of the properties of this phenomenon. So the model Hamiltonian and a non-linear master equation formalism. And last, I will talk about our main conclusions and main results related to the conductance and the spin polarization. So just to start, let's think what is usually present in systems with spin effects. So usually for having spin effects, we have atomic magnetic moments in the systems that give rise to spin orbit couplings, and also a magnetic field is present. Well, as you have seen already in this chirality-induced spin selectivity effect, none of these ingredients is present. So it was a very unexpected and surprising effect because it occurs in chiral organic molecules that are non-magnetic, and it occurs in absence of a magnetic field. So just a quick reminder on more details about what is a chiral molecule. So a chiral molecule is such that we have the original object and its specular image, and they are not connected by regular symmetry transformation like translations or rotations. So these two objects, the original one and the specular image, are the two enantiomers that the two forms that the chiral molecules can present, and they are named levo rotatory L or destro rotatory D, depends on the order of the atomic conformation, if it's clockwise or counterclockwise. So there are plenty of cis experimental evidences, as Professor Naumann told us before, related to photoemission experiments where electrons are not unbound, or also in electrochemical cells and transport experiments where the electrons are bound to the molecules. And in this talk, we are going to, well, my model will be dealing with transport experiments in particular. Also, as he said, the experiments are quite robust in its results, so even some applications have been proposed already. I let you hear some references to look at if you're interested. For example, log-of magnetization, where was mentioned by Ron, and enantiomer separations, or even hydrogen production. Well, in all experiments, the main idea is that spin polarization is a chiral induced effect. So chirality is the most relevant ingredient to take into account. And also in all experiments, there is an effect which is also very interesting from the theoretical part of view to model it, which is that spin polarization increases with the molecular length, as you can see in this graphic. And this happens for all kinds of experiments with bound or unbounded electrons. So this is the effect we want to model in the work I'm going to present in this talk related to transport experiments. And therefore I want to get a little deeper insight in these experiments. So usually for these transport experiments, we have a molecular junction performed with a chiral molecule, and we have two contacts. One is a gold contact or a metallic non-magnetic contact, and the other one is a ferromagnetic one. And the magnetization of this ferromagnetic contact can be controlled by external magnets in such a way that depending on that magnetization, you will get an up or down well, a current for electrons with a spin up or spin down, and you can get the IV curves, and you will see that these IV curves for spin ups or spin downs are different. These blue and red lines, and here also in this graphic you can see already that these numbers 26, 40, 50, they are referring to the number of base pairs of the molecule, so the molecular length. And you can see that this difference between the current up or down is increasing with the molecular length, as I told you before. So basically ideas for theoretical modeling, as Ron mentioned already, is that we have a single electron with a particular spin state propagating along the chiral molecule with a momentum p or velocity v. And also another ingredient which is typically included in models is that because we have a chiral atomic distribution, we have a chiral charge distribution in the molecule, and at the end we will have a molecular electric field that resembles that chiral symmetry. And because of this chiral field is present, then the electron in its propagation will feel a magnetic field in its rest frame. And at the end, it will there will be some spin orbit coupling affecting the electron. The magnitude of this spin orbit coupling is usually proportional to the magnitude of this field. The model Hamiltonian we used in this work is such that the radial component of the field is the most relevant one, so we forget about the rest of the components, and also the electron trajectory is considered to be helicoidal. You can see here a sketch of a helix, and this helix have some, some particular parameters. Usually the theta is the helix angle, and this phi is the twist angle. And the spin orbit coupling with these two assumptions, it will be proportional to this term here, where here these Pauli matrices that appear are the transversal components, so transversal to the trajectory of the helix, and this the component of the momentum which appears is the longitudinal one, so it's parallel to the helix. In the second quantization, the time-binding model looks like this, this formula. And here in this work, we are considering only one single chain, one molecular chain, but remember that we have two transport channels, one for the spin up and one for the spin down. In this time-binding model, we have an on-site term, some electronic hoppings connecting the spin up and the spin down channel, and this third term accounts for the spin orbit coupling. And here these Pauli matrices are coming from the transversal one of the previous slide, so it will depend on the particular, on the typical X, Y, and Z components of the Pauli matrices, but with some corrections related to the angles of the helix, the theta and the phi. These values are for DNA molecules, are typical for DNA molecules. And the spin orbit coupling will couple these two channels, the spin up and the spin down, with the nearest neighbors. So again, we are focused on this kind of transport experiment. So this is the sketch of the experiment, and this is the sketch of our model, trying to be as equal as possible. So we have the molecular part here with this tight binding Hamiltonian, and this molecular, this tight binding will be coupled to some contacts left and right through this capital gamma. And this coupling gamma can be controlled to couple to some particular spin states to simulate the ferromagnetic lead, as will show you later. So some initial considerations. In this work, we are not so interested in getting the Cis effect. So this Cis effect is already introduced in the model by taking spin-dependent electronic hoppings. So the electronic hoppings will be a matrix with two values that will be different for the spin up and spin down channels. But what we are interested in this work is to try to get the behavior that spin polarization increases with the molecular length. And this in principle cannot be obtained for regular coherent transport models. So our proposal is that because we are working with organic molecules that are very flexible, there has to be some interaction between the electron propagation and lattice vibrations of the molecules. And this effect will give us, hopefully, the spin polarization increasing with the molecular length. So the interaction between the electron and the low frequency modes will be modeled by introducing a uniform site Anderson disorder in the on-site energies. And the high frequency modes interacting with electrons will be accounted by some rate equation that I will show you now through some transition rates. So this is the master nonlinear equation or rate equation we have used to get the current along this molecular junction. It has two terms. One is the one from the molecular part, and here these transition rates W are connecting to different eigenstates labeled by mu and nu. These P are the population of the eigenstates. So with this, the rate can be performed if the state mu is filled with an electron and goes to a eigenstate mu with its empty. And here we have the non-linearity in this part. And in addition, we have another term which is related to the couple between the molecule and the leads. And here it appears again the population of the eigenstate, but also the population, the Fermi distribution at both contacts, which depends on the chemical potential of the contacts. And here, this capital gamma I mentioned before, which are the coupling between the molecule and the contacts. And as you can see, it depends on the particular spin state, sigma. So the idea is when we want to model the ferromagnetic lead, we will switch on or switch off the particular coupling gamma for a particular spin state to inject only spin up electrons or spin down electrons. We look for the stationary state of these populations, and once we have that, we can get the electrical current as a function of the voltage in the molecular junction. So because we have introduced disorder, then our eigenstates would look like that, and the low energies states will be more localized than the higher energies ones. And in order to have the electron propagation from one contact to the other, we will need to have some hoppings between these states. And these hoppings will be activated thermally. So these rates, these W's, will depend on the spectral density, which is this S, also on this function F, which contains this occupation number of the lattice mode, depending on temperature. And also these rates are proportional to the overlapping, this capital I, overlapping between two different eigenstates. And last, the coupling with the contacts will also be proportional to the coupling of the eigenstate to the to the side of the contact. And here, this small gamma are the coefficients that we will switch on and switch off to get the ferromagnetic response of the lead. Also, the chemical potentials of the leads will be shifted symmetrically with respect to the energy Fermi level of the molecule. And we will be working in the low voltage regime. So before introducing a spin orbit coupling, let's check how the model behaves and here you can see the conductance as a function of the molecular length is a double logarithm scale. And we have used different magnitudes of disorder. This W is the magnitude of disorder. So if it's 0, we have a completely ordered system. And when this W increases, then we have a more ordered system. And we consider 0 temperature and also room temperature. We can see that as long as we increase the disorder, if the temperature is 0, then the conductance will be highly reduced as expected because of the localization of the states. However, if the temperature is higher, then we can have this thermal activation paths, and then the conductance is not reduced. For any of this disorder, the conductance keeps in good values. And this, it depends also on the particular on the size of the system, because the localization length of the eigenstates has to be smaller than the system size to really see the effect of the thermal activation mechanism, because otherwise, if the localization length is of the order of the system, the eigenstates will behave more or less like extended states, and you won't see that effect. Well, if now we switch the spin orbit coupling and we consider the ferromagnetic leads, the main general trends are the same as in the previous slide, but of course we are going to have a different conductance for the spin up and for the spin down, because now we are considering that only one of these spin states is coming out from the molecular junction. But what is the most interesting result we want to show you is that it's about spin polarization. Once we have calculated the conductance for spin up and spin down electrons, we can get the spin polarization as its difference respect to the total conductance in the system. And this is what is plotted in this picture as a function of the molecular length. And the most important result is that we can obtain this spin polarization increasing with the molecular length for some particular parameters. Those are for when the solder is weak, and also when the temperature is activated. So the transport is thermally activated. And this was the behavior that all experiments showed, and we were managed to get it with this model for some particular parameters. So these are the conclusions of the talk. Respect to chiral induced spin selectivity, just to remind you that it's a very surprising effect because it occurs with non-magnetic molecules in absence of magnetic fields. One of the most surprising results in experiments is that spin polarization increases with the molecular length, and it seems that from the theoretical counterpart we need some kind of decoherence or scattering effects to get that tendency. And so our proposal to try to model that behavior, and it was successful, is that because organic molecules are flexible, the electronic transport has to be affected somehow by the lattice vibrations. So therefore we used Anderson disorder and a transition rate equation to model this kind of electron lattice interaction. And at the end, we were able to demonstrate that thermal activated transport can be the clue in weakly disordered systems to account for this behavior of the spin polarization increasing with molecular length. So this is the end of my talk. I'm open to your questions if you want. Thank you very much.
Thank you, Elena. Thank you for this beautiful talk. So now it's time for questions, please.
So far, there are no questions in the chat.
May I ask a question?
Yeah, sure, go ahead.
It's a beautiful talk. I want to ask you, can you consider case of chiral phonons where the disorder as angular momentum, how this will affect the disease?
I'm not familiar with those topics, so I couldn't say it. Sorry.
It would be interesting because chiral molecules do have chiral phonons, of course.
Yeah,
and
yeah.
This contributes angular momentum to the story, and the question, will it enhance or reduce, or what it will do? It's an interesting question.
Yeah, it's a very interesting question. We have to look at that. Yeah, thank you.
So are there more questions there in the audience?
Yeah, no more questions so far.
So then I think we can thank Elena again for this really nice and beautiful talk. And with this, we can conclude this mini colloquium on symmetry and non-linearity in low-dimensional systems. I want to thank all of you, all the audience, speakers, members of the organization for lending us the opportunity to be here and gather together. It's a pity that we could not be reunited in Madrid, so a 3D version of us could have been way better than this, but Having said that, I think it's been a great success. I do hope that you will continue enjoying the conference, and I hope to see you around. Well, you can come and visit us in Salamanca. Salamanca is your place. So if you want to come and see this beautiful city, well, it's open for everyone. Thank you so much. Have a really wonderful rest of the conference.
Yeah, thank you very much to everyone.